Welcome. This is going to be the first lecture in the reinforcement learning track of this course. Now, as Tori will have explained, there are more or less two separate tracks in this course. Of course, overlap between the deep learning side and the reinforcement learning side. Wait, let me just turn this off in case. But they can also be viewed more or less separately. And some of the things I will be talking about will tie into the deep learning side. Specifically, we will be using deep learning methods and techniques at some points during this course. But a lot of it is separable and can be studied separately and has been studied in the past for many, many years separately. This lecture specifically, I will take a high-level view and cover lots of the concepts of reinforcement learning. And then in later lectures, we will go into depth into several of the topics. So if you feel there's information missing, yes, that's definitely the case. However, if you feel unduly confused, feel free to stop me and ask questions at any time. There are no stupid questions. If you didn't understand something, it's probably because I didn't explain it well, and there's probably loads of other people in the room that also didn't understand it the way I intended. So feel free to ask questions at any time. I'll also have a short break in the middle, just to refresh everybody. Okay, so let's dive in. I'll start with some boring admin, just so we can warm up. Schedule-wise, most of the reinforcement learning lectures are scheduled at this time. Not all of them. There's a few exceptions, which you can see in the schedule on Moodle. Of course, the schedule is what we currently believe it will remain, but feel free to keep checking it in case things change. Or just come to all lectures and then you never miss anything. So check Moodle for updates. Also use Moodle for questions. We'll try to be responsive there. As you will know, grading is through assignments. And the background material for specifically this reinforcement learning side of the course will be the new edition of the Sutton and Bartow book. A full draft can be found online. And I believe it is currently or will very soon be in press if you prefer a hard copy, but probably not in time for this course. But you can just get the whole PDF. Specifically for this lecture, the background will mostly be chapters 1 and 3. And then next lecture, I will actually cover more out of chapter 2. I especially encourage you to read chapter 1, which gives you a high-level overview, the way Rich thinks about these things, and also talks about many of these concepts, but also gives you a large historical view on how these things got developed, which ideas came from where, and also how these ideas changed over time. Because if you get everything from this course, you'll have a certain view, but you might not realize that things may have been perceived quite differently in the past, and some people might still perceive quite differently right now. So I'll mostly give my view, of course, but I'll try to keep as close as possible to the book. And I think our views overlap quite substantially anyway, so that should be good. So this is the outline for today. I'll start by talking just about what reinforcement learning is. Many of you will have a rough or detailed idea of this already, but it's good to be on the same page. I'll talk about the core concepts of a reinforcement learning system. One of these concepts is an agent, and then I'll talk about what are the components of such an agent. And I'll talk a little bit about what are challenges in reinforcement learning, so what are research topics or things to think about within the research field of reinforcement learning. But of course, it's good to start with defining what it is. But before I do that, I'll start with a little bit of motivation. And this is a very high-level abstract view, maybe. But one way to think about this is that first, many, many years ago, we started automating physical solutions with machines. And this is in the Industrial Revolution. Think of replacing horses with a train. We kind of know how to pull something forward across a track, and then we just implement that machine. And we use then the machine instead of human or, in the case of horses, animal labor. And of course, this created a huge boom in productivity. And then after that, second wave of automation, which is basically still happening, but has been happening for a long while now, is what you could call the digital revolution, or is sometimes called the digital revolution, in which we did a similar thing, But instead of taking physical solutions, we took mental solutions. So maybe a canonical example of this is a calculator. We know how to do division, so we can program that into a calculator and then have it do that mental, what used to be a purely mental task, on a machine in the future. So we automated mental solutions. But we still, in both of these cases, came up with the solutions ourselves. Right? We came up with what we wanted to do and how to do it, and then we implemented it in a machine. So the next step is to define a problem and then have a machine solve it itself. For this, you require learning. You require something in addition, because if you don't put anything into the system, how can it know? One thing you can put into a system is your own knowledge. This is what was done with these machines, either for mental or physical solutions. But the other thing you could put in there is some knowledge on how to learn, but then the data, having the machine learn for itself. So what is then reinforcement learning? There are still, by the way, a couple of seats sprinkled throughout the room, so feel free to try and grab one, because it's getting rather busy. Okay, so what is specific about reinforcement learning? So I'll posit that we and many other intelligence beings, or beings that we would call intelligence, learn by interacting with an environment. And this differs from certain other types of learning. For instance, it is active rather than passive. You interact, the environment responds to your interaction, and this also means that the interactions are often sequential, right? The environment might change because you do something, or you might be in a different situation within that environment, which means that future interactions can depend on earlier ones. And these things are a little bit different from, say, supervised learning, where you typically get a data set and it's just given to you, and then you just crunch the numbers essentially to come up with the solution. This is still learning, right? This is still getting new solutions out of the data, but it's a different type of learning. In addition, many people agree that we are goal-directed, so we seem to be going towards certain goals, maybe also without knowing exactly how to reach that goal in advance. And we can learn without examples of optimal behavior. Obviously, we can also learn from examples, as in education, but we often also just learn by trial and error, and that's going to be important. So this is a canonical picture of reinforcement learning. There's many versions of this. There is an agent, which is our learning system, and it sends certain actions or decisions out. These decisions are absorbed by the environment, which is basically everything around the agent, even though I drew them. It's mostly done in these figures. But you can think of the environment as just everything that is outside of the agent. And the environment responds, in a sense, by sending back an observation. If you prefer, you can also think of this as maybe more of a pull action by the agent, that the agent observes the environment, whatever it is. And then this loop continues. The agents can take more actions, and the environment may or may not change depending on these actions, and the observations may or may not change. And the idea is then to learn within this interactive loop. So, in order to understand why we want to do learning, it's good to realize that there's distinct types of learning. I already mentioned the difference between active learning and passive learning, but there's also different goals for learning. So two goals that you might differentiate is, one is to find previously unknown solutions. Maybe you don't care exactly how you arrive at these solutions, but you might find it hard to code them up by hand or to invent them yourself, so you might want to get this from the data. But it's good to realize that this is a different goal from being able to learn quickly in a new environment. And both of these things are valid goals for learning. So in the first type of learning, an example might be that you might want to find a program that can play the game of Go better than any human, which is a goal to find a certain solution. In the second type of learning, you might think of an example where a robot is navigating terrains, but all of a sudden it finds itself in a terrain that it has never seen before and also wasn't present when people built the robot or when the robot was learning. Then you want the robot to learn online, and you want it to maybe adapt quickly. Reinforcement learning as a field seeks to provide algorithms that can handle both these cases. Sometimes they're not clearly differentiated, and sometimes people don't clearly specify which goal they're after, but it's good to keep this in mind. Also note that the second point is not just about generalization. It's not just about oh, you learn about many terrains and then you get a new one and you're able to deal well with it. It's about that a little bit, but it's also about being able to learn online to adapt even while you're doing it. And this is fair game. We do that as well. When we enter a new situation, we do adapt still. We don't have to just lean on what we've learned in the past. So another way to phrase what reinforcement learning is it is the science of learning to make decisions from interaction. And this requires us to think about many concepts, such as time, and related to that, the long-term consequences of actions. It requires us to think about actively gathering experience because of the interaction. You cannot assume that all the relevant experience is just given to you. Sometimes you must actively seek it out. It might require us to think about predicting the future in order to deal with these long-time consequences. And typically it also requires us to deal with uncertainty. The uncertainty might be inherent to a problem. For instance, you might be dealing with a situation that is inherently noisy, or it might be that certain parts of the problem that you're dealing with are hidden to you. For instance, you're playing against an opponent and you don't know what goes on in their head. Or it might just be that you yourself create some uncertainty because you don't know, maybe you're following a behavior that sometimes is a little bit stochastic, so you can't predict the future with complete certainty, just based on your own interaction. I'm just going to repeat once more. There's still a few seats if people want to grab them. One back there, there's a few up here. So there's a huge potential scope for this because decisions show up in many, many places if you think about it. And so one thing that I just want you to think about is whether this is sufficient to be able to talk about what artificial intelligence is. Now, of course, I could take a stand here. This is just to provoke you to think about that. Can you think of things that we're not covering, right? That you might need for artificial intelligence? That's basically the thing that I want you to think about. And if so, we should probably add them. So there's a lot of related disciplines, and reinforcement learning has been studied in one form or another many times and in many forums. This is a slide that I borrowed from Dave Silver, where he noted a few of these disciplines. There might be others, and these might not even be might not be the only, might not be the best examples, although some of them are pretty persuasive. And the disciplines that he pointed out were at the top computer science, which a lot of you will be studying some variant of, in which we might do something called machine learning, and you could think of reinforcement learning as being part of that discipline. I'll come back to that later. But also in neuroscience, people have investigated the brain to large extents and found that certain mechanisms within the brain look a lot like the reinforcement learning algorithms that we'll study later in this course. So there might be some connection there as well, or maybe you can use these concepts that we'll talk about to understand how we learn. Also in psychology, maybe this is more like a higher level version of the neuroscience argument, where there's behavior, obviously, there's decisions, and maybe you can reason about that. Maybe you can model that in a very similar way, or maybe even the same way as you can model a reinforcement learning problem. And then think about learning, what that entails, how the learning progresses using this framework. Separately, on the other side, you have engineering. Sometimes you just want to solve a problem, and there are many decision problems out there that people want to solve for many different reasons, but typically to optimize something. And within that, we have a field called optimal control, which is very closely related to reinforcement learning, and many of the methods overlap, although sometimes the focus is a little bit different and the notation might be a little bit different. Fairly similarly, in mathematics, there's a subcategory, or maybe I don't know whether it's completely fair to say that it's part of mathematics. Maybe it's a little bit more like a Venn diagram itself, called operations research. And operations research, this is the field where you basically look for solutions for many problems using mathematical tools, including Markov decision processes that we'll touch upon later in this course, and dynamic programming and things like that, which are also used in reinforcement learning. Finally, at the bottom, it says economics, but there's other related fields that you might consider here. One thing that's quite interesting about this is that it's very clearly a multi-agent setting. So now there's multiple actors in a situation, and together they make decisions, but also separately. And there's all these interesting interactions between these agents. And it's also quite natural in economics to think about optimizing something. Many people talk about optimizing, say, returns or value. And this is very similar to what we'll discuss as well. So to zoom in a little bit on the machine learning part, Sometimes people make this distinction, that machine learning basically has a number of subfields. Maybe the biggest of this is the supervised learning subfield, which we're getting quite good at, I would say. And a lot of deep learning work, for instance, is done on supervised settings. The goal there is to find a mapping. You have examples of inputs and outputs, and you want to learn that mapping. And ideally, you want to learn a mapping that also generalizes to new inputs that you've never seen before, in a nutshell. Unsupervised learning, separately, is what you do when you don't have the labeled examples. So you might have a lot of data, but maybe you don't have clear examples of what the mapping should be, and all that you can do or all that you want to do is to somehow structure the data so that you can reason about it, or that you can understand the data itself better. Now, reinforcement learning, some people sometimes perceive that as being part of one of these, or maybe a little bit of a mixture of both. But I would argue that it's different and separate. And in reinforcement learning, one of the main distinctions is that you get a reinforcement learning signal, which we call the reward, instead of a supervised signal. What this signal gives you, and I'll talk about it later more, is some notion of how good something is compared to something else, but it doesn't tell you exactly what to do. It doesn't give you a label or an action that you should have done. It just tells you, I liked this much. But I'll go into more detail. So characteristics of reinforcement learning, and specifically how does it differ from other machine learning paradigms, include that there's no strict supervision, only a reward signal, and also that the feedback can be delayed. So sometimes you take an action, and this action much later leads to reward. And this is also something that you don't typically get in a supervised learning setting. Of course, there's exceptions. In addition, time and sequentiality matters. So if you take a decision now, it might be impossible to undo that decision later. Whereas if you just make a prediction and you update your loss in a supervised setting, typically you can still redo that later. This means that earlier decisions affect later interactions, and it's good to keep that in mind. And basically the next lecture also talks a lot about this. So examples of decision problems, there is many, as I said. Some concrete examples to maybe help you think about these things include to fly a helicopter, or to manage an investment portfolio, or to control a power station, make a robot walk, or play video or board games. And these are actually examples where reinforcement learning has been, or versions of reinforcement learning have been applied. And maybe it's good to note that these are reinforcement learning problems because they are sequential decision problems, even if you don't necessarily use what people might call a reinforcement learning method to solve them. It's good to make that distinction because some people, they think of the current reinforcement learning algorithms and they basically unify the field with those specific algorithms. But reinforcement learning is both a framework of how to think about these things, and there's a set of algorithms which people talk about as being reinforcement learning algorithms. But you could be working in a reinforcement learning problem without using any of those algorithms specifically. So I mentioned a few of these already, but core concepts of a reinforcement learning system are the environments that the agent is in, a reward signal that specifies the goal of the agent, and the agent itself, of course. The agent itself might contain certain components, and I'm going to go through all of these in the rest of this lecture. But note that in the interactions figure that I showed before, this is the same one. I actually didn't put the reward in, and there's a reason I did that, because most of these figures that you'll see in literature actually have the reward going from the environment into the agent, and that's fair. And in that case, the agent itself basically is only the learning algorithm. That means that if you have a robot, the learning algorithm sits somewhere within that robot, but the agent in this picture is not the same as the robot as a whole. The learning algorithm can perceive part of the robot as its environment in a sense. Because typically, the environment doesn't care. It doesn't have a reward. It doesn't have that notion. Typically, it's us that specify a reward, and it lives somewhere within your reinforcement learning system. That's why I didn't put it in the figure, because you can think of it as coming from the environment into the agent, or you can think of it as part of the agent, but not part of the learning algorithm. Because if the learning algorithm can modify its own reward, then weird things could happen, and it could find ways to optimize its reward, but only because it's setting it, not because it's learning anything interesting. So it's useful to think of the reward as being external to the learning algorithm, even if it's internal to the system as a whole. So what happens here, this is the interaction loop that I was talking about. If we introduce a little bit of notation, at each time step t, the agent will receive some observation, which is a random variable, which is why I use capital O there, and a reward from somewhere, capital R, and the agent then executes an action, capital A. The environment receives this action, and you can either think of it as emitting a new observation and a new reward, or you can just think of the agent as receiving that, as pulling that from the environment. But for now, we'll just talk about it as if the environment just gives you that back as a function. It takes in the action, and it returns you the next observation and the next reward. This is a fairly simple setup, fairly small in some sense, but it turns out to be fairly general as well, and we can model many problems in this way. So the reward, specifically, is a scalar feedback signal. This indicates how well the agent is doing at a step time t, and therefore it defines the goal, as I said. Now the agent's job is to maximize the cumulative reward, not the instantaneous reward, but the reward over time. And we will call this the return. Now this thing trails off into the end there. I didn't specify when it stops. The easiest way to think about it is that there's always a time somewhere in the future where it stops, so that this thing is well defined and finite. A little while later I'll talk about when that doesn't happen, when you have a continuing problem, and then you can still define a return that is well defined. And reinforcement learning is based on the reward hypothesis, which is that any goal can be formalized as the outcome of maximizing a cumulative reward. It's basically a statement about the generality of this framework. Now, I encourage you to think about that, whether you agree that that's true or not, and if you think it's not true, whether you can think of any examples of goals that you might not be able to formalize as optimizing a cumulative reward. To maybe help you think about that, I'd like to note that these reward signals, they can be very dense. There could be a reward on every step that is non-zero, but they could also be very sparse. So if a certain event specifies your goal, you could also just get a positive reward whenever that happens, and 0 rewards on every other step. And that means that then there is a reward function that models that specific goal. So the question is whether that's sufficiently general. I haven't been able to find any counterexamples myself, but maybe you do.
Excuse me?
Yeah.
Does the reward have to be positive?
No, that's a very good question, sorry. We use the word reward, but we basically mean it's just a real valued reinforcement signal. And sometimes we talk about negative rewards as being penalty. This is especially common in psychology and neuroscience. In the more computer science view of reinforcement learning, we typically just use the word reward, even if it's negative. And then indeed you can have things that push you away from certain situations that you don't want to repeat. I'll give an example. I'll revisit this example a little bit later, but maybe it's good to give it now as well. You could think of a maze where you want to exit the maze. So the goal is to exit the maze. Then there's multiple ways to set up a reward function that encodes that. One is, as I said just now, just give 0 rewards on every step, but give a positive reward when you exit the maze. But what you could also do is just give a negative reward on every step, and then stop your episode when you exit the maze. And then minimizing that negative, maximizing your reward means minimizing the absolute negative rewards. So it still encodes the goal of getting out of the maze as quickly as possible. You could think of one as being chasing the carrot and one as avoiding the stick. To the learning algorithms, it typically doesn't matter too much. Or at least to the formalism of the learning algorithms. In practice, of course, everything matters, but okay. So now that we have returns, we can talk about predicting those returns. And to do that, we first have to talk about values. So the expected cumulative reward, which is basically the expected return, as we defined it just now, is what we call the value. And the value is, in this case, a function of state. So the expectation here is given conditional on the state that you put in into the function, and then over anything that's random. The goal is then to maximize this expected value rather than the actual instantaneous value or the random value, because typically you don't know the random value yet, by picking suitable actions. So the rewards and the values both define the desirability of something, but you could think of the reward as defining the desirability of a certain transition, like a single step, And then the value is defining the desirability of this state more in general, into the indefinite future, potentially. Also note, because we'll be using that quite a bit in this course, that the returns and the values can be defined recursively. So I put it down here for the return. The return at a time step t is basically just the one-step reward and then the return from there. And that turns out to be something that we can usefully exploit. So I said the goal is then to pick action, so we have to talk a little bit about what that then means. So again, the goal is to select actions as to maximize the value, basically from each state that you might end up in. And these actions might have long-term consequences. What this means in terms of the reward signal is that your immediate reward for taking an action might be low or even negative, but you might still want to take it if it brings you to a state with a very high value, which basically means you'll get high rewards later. So that means it might be better to sacrifice immediate reward to gain more long-term reward. And examples of this include, say, financial investment, where you first pay some money to invest in something, but you hope to get much more money back later. Refueling a helicopter, you might not gain anything specifically related to your goal from doing that, but if you don't, maybe your helicopter will at some point not work anymore. And in, say, playing a game, you might block an opponent's move. Rather than going for the win, you first prevent the loss, which might then later give you a higher probability of winning. In any of these cases, the mapping from states to action we'll call a policy. So you can think of this as just being a function that maps each state into an action. It's also possible to condition the value on actions. So instead of just conditioning on the state, you can condition on the state and action pair. The definition is very similar to the state value. There's a slight difference in notation. For historical reasons, this is called a Q function. So for states, we use V, and for state action pairs, we use Q. There's really no other reason than just historical for that. And we'll talk in depth about these things later. So the only difference here is that it's now also conditioned on the action. Otherwise, the definition is exactly the same as before. Okay, if everybody's on board, I'll now talk about agent components. And I'll start with the agent state. There's still a little bit of room in the room if somebody still wants to grab a chair. People are not too uncomfortable. Thanks. So the first, I talked a little bit already about states, but I didn't actually say what a state is. I trusted that you would have some intuitive notion of it. So I'll talk about what an agent state is. So as I said, a policy is a mapping from states to actions, or the other way to say it, the actions depend on some state of the agent. Both the agent and the environment might have an internal state, or typically actually do have an internal state. In the simplest case, there might only be one state, and both environment and agent are always in the same state. And we'll cover that quite extensively in the next lecture, because it turns out you can already meaningfully talk about some concepts, such as how to make decisions when only considering a single state. And it just abstracts away all the issues of sequentiality and states and everything. But the whole next lecture will be devoted to that. But often, more generally, there are many different states, and there might even be infinitely many. So what do I mean when I say infinitely many? Just think of it as being, there's some continuous vector as your state. And maybe it can be within some infinite space just because you don't know exactly where it's going to be, and it can basically be arbitrarily anywhere in that state. And then you are in basically a typical domain where deep learning also shines, where you can maybe generalize across things that you haven't seen because things are sufficiently smooth in some sense. So the state of the agents generally differs from the state of the environment. But at first we're going to unify these, as I'll explain later. But it's good to keep in mind that in general the agent might not know the full state of the environment. So the state of the environment is basically everything that's necessary for the environment to return its observations and maybe rewards, if those are part of the environment. And like I said, it's usually not visible to the agent, but even if it is visible, it might contain lots of irrelevant information. So even if you think about, say, if you think about the real world, us or a robot operating in the real world. Even if you could know all the locations of all the atoms and all other things that might be relevant in some way to your problem, you might not want to or even can process all of that. So it still, in that case, makes sense to have an agent state that is smaller than the full environment state. So instead, the agent has access to a history. It gets an initial observation, and then this loop starts. You take an action, you get a reward in a new observation, you take another action, and so on and so on. In principle, the agent could keep track of this whole history. It might grow a bit big, but we could imagine doing that. And an example of such a history might be the sensory motor stream of a robot, just all the things that ever happened to the robot. So this history can then be used to construct an agent state. And the actions then depend on that state. In the fully observable case, we assume that the agent can see the full environment state. So the observation is now equal to the environment state. This is especially useful in smallish problems where the environment is particularly simple. But it occurs sometimes in real practice. For instance, if you think about playing a game, a single-player board game where you can see the whole board, this might be such a case. Or even if you play a multiplayer board game but you have a fixed opponent, this might again be the case. If you're playing against an unknown opponent, it's no longer the case because you cannot look inside the head of the opponent. If this is the case, then the agent is in the Markov decision process. And I'll define that. Many of you might know what this is, but Markov decision processes are essentially a useful mathematical framework that you're going to use to reason and talk about a lot of the concepts in reinforcement learning. It's much easier to reason about than the full problem, which is non-Markovian, as I'll talk about in a bit. But it's also a little bit limited because of the Markov assumption. So what does it mean to be Markov? So decision process is Markov, or Markovian, if the probability of a reward and subsequent state, I've written it down here as the new Sutton and Bartow edition also does, as a joint probability of the reward and the state. The way they depend on your current state and action is fully informative if you would condition, for the case if you would condition on the full history. What that means is that the current state gives you all the information you need to basically predict the next reward and the next state. So if this probability is fixed, even if you don't know this probability, I'm not claiming that the agent knows it, but if it exists and if it's fixed, then it's a Markov decision process. Intuitively, it means that the future is independent of the past given the present, where the present is now your state. So in practice, this is very nice and useful because it means that when you have this state, you can throw away the history. And the history can grow unboundedly. So that's something that you don't want to keep doing. So instead, you much prefer the case where you can just throw away everything and you just keep that state. Another way to phrase it is it's a sufficient statistic for the history. The environment state typically is Markov in most cases. There are exceptions to this. For instance, if you think of a non-stationary environment. But typically, you could think of the environment state as being Markovian, but you're just not being able to perceive it. So things might appear non-stationary, even if they aren't. The history itself is also Markovian, because, of course, if you condition on the history, or you condition on the history, that's the same thing. But it's going to grow big. More commonly, we're in a partial observable case. This means that the agent gets partial information about the true state. And examples of this include a robot with camera vision that is not told its absolute location or what, say, is behind the wall. Or, say, a poker playing agent, which only observes public cards. So there's multiple ways that second one is partially observable. One is the fact that it can't see the cards of the opponents, and the other is the fact that it can't see within the brain of the opponents. And formally, these things are then called partially observable Markov decision processes. There's a lot of literature on these, and especially on solving these exactly. A lot of that we're not going to cover, but it's good to keep in mind that this is actually the common case, that you just get some observations, but they don't tell you the full state. Doesn't mean you want to use the solution methods necessarily from the literature on partially observable Markov decision processes, especially those who solve these things exactly, because that tends to be a very hard and interesting problem, but it also tends to be quite computationally expensive. And again, the environment state can still be Markov even if you only get a partial observation of this, but the agent just has simply no way of knowing this. Is that clear? Okay, so now we can talk about what the agent state then is. So the agent state, as I said before, is a function of the history. The agent action depends on the state, so it's important to have this agent state. And a simple example is if you just make your observation the agent state. More generally, we can think of the agent state as something that updates over time. You have your previous agent state, you have an action, a reward, and an observation, and then you construct a new agent state. Note that, for instance, building up your full history is of this form. You just append things. But there's other things you could do. You could, for instance, keep the size of the state fixed rather than have it grow over time, as you would do with a history. Here, what I denoted with f is sometimes called the state update function. And it's an important notion that we'll get back to later. It's actually also a very active area of research. How do you create such a state update function that is useful for your agent, especially if you cannot just rely on your observations? So the agent state is typically much smaller than the environment state, and it's also typically much smaller than the full history, just because of computational reasons. And here's an example. So let's assume a very simple problem where this is the full state of the environment. There's a maze. Maybe it's not the full state. Maybe there's also an agent in the maze that I didn't write down. But let's say that this is your full state of the maze. And let's say there is an agent, and it perceives a certain part. So the observation is now partial. The agent doesn't get its coordinates. It just sees these pixels, say, as an example. Now what might happen is that the agent walks around in this maze and all of a sudden, sometime later, finds itself in this situation. Now this is an example of a partial observable problem because both of these observations are indistinguishable from each other. So just based on the observation, the agent has no way of knowing where it is. So a question for you to ponder a little bit. How could you construct a Markov agent state in this maze for any reward signal? Because I didn't specify what the reward signal is. If you want, you can just think up one. Maybe there's a goal somewhere. Does anybody have a suggestion?
The previous state, just seeing where you are now, minus seeing where you were before, sort of thing.
Right. So indeed, in this case, you'd have to carefully check for the specific maze whether that's sufficient. It might be sufficient. It might depend on your policy. If you have an action that stands still, it might not be enough because you might see the same observation twice. If that action doesn't exist, in this maze, it might actually be enough. I didn't carefully check. But the more general idea, which I think is the good idea here, is that you use some part of your history to build up an agent state that somehow distinguishes these two situations. If you do have a certain policy, it might be that in the left state you always came from above and in the right state you always came from below, and just having that additional information, what the previous observation was, might just be enough to completely distinguish these situations. And that is indeed the idea of a state update function. This would be a simple state update function that just concatenates the previous two, and each time you see a new observation, you toss away the oldest one. And that's actually something that is done quite frequently. For instance, in the Atari games that you saw before, there was just a concatenation of a couple of frames, and this was the full agent state. So it was basically just an augmented observation. Yeah?
So on the last slide, you've got O at t plus 1.
Mm-hmm.
Rather than O at t.
Which one? Here. Yeah, so in the ordering here is that you're in a certain state, ST. Based on this state, you take an action, AT, and then we consider time to tick after you take the action, basically when you send things to the environment. This is just a convention. Actually, some people write down RT rather than T plus 1, so be aware. But we'll take the convention that basically the time steps when you send that action to the environment. Then the reward and the new observation come back, and we can consider the next agent state, st+1, as being a function of this new observation, so that when you take your next action, you can already take your observation into account. If it would be OT rather than OT+1, then you couldn't take your newest observation into account when taking your next action. It's a good question. So I said many of these things already, but to summarize, to deal with partial observability, the agent can construct a suitable state representation. And examples of these include, as I said before, you could just have your observation be the agent state. But this might not be enough in certain cases. You could have the complete history as your agent state, but this might be too large, might be hard to compute with this full history. Or you might, as a partial version of the one I showed before, you could have some incrementally updated states, which maybe only looks at the observations, maybe ignores the rewards and the actions in this example. But if you write it down like this, maybe you'll notice that this looks fairly remarkably similar to a recurrent neural network, which I know we haven't yet covered in the deep learning side, but we will. And basically, the update there looks exactly like this. So that kind of already implies that we can use maybe a deep learning technique here of the recurrent neural networks to implement this state update function. And indeed, this has been done. So sometimes the agent state, for this reason, is also called the memory of the agent. We use the more general term for the agent state, which maybe includes the memory and maybe also additional things if you want to think about it like that. But you can think of the memory as being an essential part of your agent state, especially in these partially observable problems. Or alternatively, you can think of memory as a useful tool to build an appropriate agent state. So that wraps up the state bit. Feel free to inject any questions. And otherwise, I'll continue with policies, which is fairly short. So the policy just defines the agent's behavior, and it's a map from the agent state to an action. There's two main cases. One is the deterministic policy, where we'll just write it as a function that outputs an action. State goes in, action goes out. But there's also the important use case of a stochastic policy, where the action is basically, there's a probability of selecting each action in each state. Typically, we will not be too careful in differentiating these. So you can just think of the stochastic one as the more general case, where sometimes the distribution just happens to always select the same action, and then you already covered the discrete case, the deterministic case, sorry. Note that I didn't specify anything about what the structure of this function is, or what even the structure of the action is. In the beginning of the course, we'll mostly focus on the case, and actually throughout the course, we'll mostly focus on the case where these actions can be thought of as being part of a discrete set. For instance, if you think of the joystick used in the Atari games, it basically had up, down, left, right, shoot, and those type of actions, but it didn't have move your motor a little bit in this direction. We call that a continuous action, and there's also algorithms that can deal with those. For notation, it doesn't really matter. It's just a function that outputs either, maybe you can think of it as an integer for the discrete case, and maybe it's a vector or a real valued number for the continuous case. I'm not talking yet about how to learn these things. This will be later in the course. Which means we can then move on, because there's a lot to be said about learning policies, but not too much about what a policy is. And we'll move on to the value functions. So as said before, the actual value function is just the expected return, conditioned on the state, and something that I actually didn't talk about before, but it's also conditioned on a policy. I basically hid that on the previous slide. There's another thing that I hid, which I'm introducing here, which is a discount factor. So the return now is redefined. It's a slightly different return from before. There's this gamma in between. If the gamma is equal to 1, it's the same as before. It's just your accumulation of rewards into the future. In many cases, we actually pick a gamma that is slightly less than 1. And what that does is it trades off immediate rewards versus long-term rewards, putting a higher weight on the immediate rewards. Basically, you're downweighing or discounting, and this is why it's called a discount factor, the future rewards in favor of the immediate ones. If you think of the maze example that I said earlier, where you get a 0 reward on each step, but then you get, say, a reward of +1 when you exit the maze, if you don't have discounting, the agent basically has no incentive to exit the maze quickly. It would just be happy if it exits the maze in some time into the future. But when you have discounting, all of a sudden the trade-off starts to differ, and it'll favor to be as quick as possible, because then the exponent on this gamma will be smaller. If it takes fewer steps to go to the exit, it will have discounted this future return less. So the value depends on the policy, as I said, and it can then be used to evaluate the desirability of states, one state versus the other, say. And therefore it can also be used to select between actions. You could say plan one step ahead. You could use your value. It's actually more convenient in that case, although I didn't put it on the slide, to use these action values, because those immediately give you access to the value of each action. This is just a definition of the value. Of course, we're going to approximate these things later in our agents, because we don't have access basically to the true value typically. Oh, there's a plus sign missing there on the top. It should have been reward plus 1 plus the discounted future return gt plus 1. I'll fix that before the slides go onto Moodle. And I said this before for the undiscounted case, but now I'm saying it again for the discounted case. The return has a recursive form. It's a one-step reward plus the remaining return, but now discounted once. And that means that the value also has a recursive form, because we can just write down the value as the expectation of this return. But then it turns out, because the expectation can be put inside as well, over this gt plus 1, this is equivalent to just putting the value there again. And this is a very important recursive relationship that we'll heavily exploit throughout the course. And notation-wise, note that I'm writing down A as being sampled from the policy. So this is basically assuming stochastic policies, but like I said, deterministic can be viewed as a special case of that. And then the equation is known as the Bellman equation by Richard Bellman from 1957. There's a similar equation, interestingly, for the optimal, which is the highest possible value for any policy. And this equation is written down there. It basically takes the action that maximizes the one step and then uses the optimal value on the next step. So it's, again, recursively defined. And you could essentially view this as a system of equations. If there's a limited number of states and a limited number of actions, this is just a system of equations that you could solve. And thereby, you can get the optimal values and the optimal policy. In order to do that, you need to be able to compute this expectation, and that's something that we'll cover later as well. And you'll use dynamic programming techniques then to solve this.
Could you just explain the recurrency again? So, like the value of a particular state depends on the cumulative reward?
Mm-hmm. Yeah, sorry, it's basically the top line there, which is missing the plus, unfortunately. But it's basically based on the recurrence of the return, which I assume is somewhat clearer, that you can just split up the return into a single reward and then the rest of the return, which is again accumulation of rewards, in order to then get the recursive form of the value, especially for the for this case. It's enough to note that the expectation on the top line, because it's already an expectation about the future, you can put the expectation around this internal return there, which means it's just defined as the value. This is just a nested expectation then, but that's equivalent. So you can also write this down very explicitly with just sums over probabilities of landing in each state. And we will get back to that later. So I'll give you some explicit formulas also to show that this recursion holds. Not in the next lecture, but in the lecture after that.
So
yeah.
If you have 10 time steps, do you want to maximize the reward that you have, the cumulative reward you have at the end, or do you want to maximize the sum across all 10 time steps?
Let me rephrase to see if I understood the question correctly, which is if you're looking ahead from a certain state, you want to consider 10 steps into the future. The question is whether you want to optimize for right now or you want to optimize for on each of these steps. Is that?
If you want to maximize for the last time point or for each of the steps.
So on each state, you basically want to follow the policy that optimizes the return from that state, the expected return from that state. That essentially means that in the last state, you'll want to do the optimal thing, but in the state before, you want to do the optimal thing conditioned on the fact that in the last state, you're going to do the optimal thing. So that's also, in that sense, recursive. There's a different matter here, which maybe just to clarify, there's also a question of which states you care about. Do you care about behaving optimally from this state, or do you care about behaving optimally from all states? If you can solve everything exactly, you can actually have both. You can just be optimal from every state that you can possibly be in. Later, when we're going to start approximating things, you're going to have to pick. Which states do I care about? Which states don't I care about? And then you might care more about having good solutions in certain states rather than in other states. Yeah?
Does that mean that we recurse back to the very end of the problem and then work our way back to a state now when we want to take a decision?
Yeah, so the question is, can you then solve this by recursing backwards, starting at the end, and then just finding, I mean, that's a simpler problem in a sense, because then you just look at the instantaneous reward if you're at the end, and you pick the action that optimizes the instantaneous reward, and this will give you the optimal value of that state. And then indeed, this is a valid and often used solution technique to then iterate backwards. What you could also do, and I'll talk about that in much more depth, is just look at all states at the same time and use these recursive definitions to basically incrementally go towards the solution. So you could either indeed start at certain states, say at the end, and then recurse backwards, and that might be more efficient, or you could just do all of them at the same time and you'll still get to the optimal solution. Yeah?
So you're using expectation there, but in a lot of real world situations, the agent will care more about the shape of probability distribution at the end of the period, not necessarily expectation. So if you're looking at investments, you care much more about not going bust, you do about eking out a tiny bit of extra return.
Yeah.
So does that fit the framework, or does it ruin expectation and narrative?
So it's a very good question. So the question is, here we're approximating expected cumulative rewards or expected returns, but sometimes you care more about the whole distribution of returns. And this is definitely true. And it's actually, it hadn't been studied that much. So there's been quite a bit of work on things like safe reinforcement learning, where people, for instance, want to optimize the expected return, but conditional on not ever having a return that is lower than a certain thing. But recently, and with that I mean like last year, a paper was published on distributional reinforcement learning, where the distribution of returns is explicitly modeled. This has been done, there's a little bit of prior work on that, but actually not as much as you might think. And it turns out you could do very similar things with recursive definitions in that case. And then indeed, modeling that distribution is in some cases very helpful. You can help it to steer your decision away from risky situations, or sometimes you actually want to be, so that would be called risk averse, say in economics lingo, or you could be more risk seeking, which could also sometimes be useful, depending on what you want to achieve. So yes, very good question. That's very current research. Yeah?
When you're taking the maximum over the expectation with respect to A here, could we think of it as you're kind of marginalizing out A and then taking the maximum of the resulting distribution?
We're not marginalizing it, we're literally maximizing over it, which is a little bit different. But it's in some sense it's similar, in the sense that you get rid of the dependence on A and therefore of the policy. And therefore this whole recursively defined value no longer depends on any policy, because we're going to do this max on each step. You could similarly think of marginalizing on each step, but that's slightly different, because marginalizing would take the distribution into account, but here you still have to have a distribution then, which is your policy then, the distribution over actions. But in this case, we're not interested in a fixed distribution over actions, a fixed policy, but instead we're choosing to maximize over it. But yes, it's otherwise it's very similar. Yeah?
Just to check out if I understood. In practice, in reinforcement learning, there's lots of problems where you have a continuous time domain or something. So you can't just recurse infinitely into the future. So in practice, a lot of the time you must have to come up with approximations to the value function, right?
Yes, so that's two parts of that question. One is how to deal with continuous domains, for instance, continuous time. And the other one is how to deal with approximations, because even if you don't have continuous time, the state space, for instance, might be huge, and that also might require you to approximate. So approximations are going to be very central in this course, and we're going to bump into them all the time. Also, if everything's very small, you'll still have approximations in the sense that you don't know these values, and if you can't compute the expectation, because you don't know the model of the environment, then you still have to approximate these values. And you could do this with sampling, simply. But then there's ways to sample which are more efficient than others, and learning algorithms that are more efficient than others. On the continuous time points, the Bellman equation is actually, that's one. There's also a different one called the Hamilton-Jacobi-Bellman equation, or sometimes the Hamilton-Jacobi equation, which is basically the continuous time variant of this. That one's more often studied in control theory and control problems, where typically a lot of things are more continuous, but then also typically people make more assumptions about the problems, which then allows them to solve these things. It basically becomes, again, a system of equations, but now with infinite inputs and outputs, but you can still solve these things if you make suitable assumptions about the problem. We'll not touch upon that much in this course, but I'll be happy to give you pointers if you want. Yeah?
Sorry, could you just repeat what the difference is between the value and the return?
Yeah, the return is the actual thing that you see, so it's random, it's sampled, and then the value is the expectation of that. Thanks. Yeah?
The environment state, do people always model it as being Markov, even if it's not observable?
No. I actually already gave an example. So sometimes people set up an environment in which these probabilities change over time, which means it's already not Markov. We would call that a non-stationary environment. In that case, you could still, I mean, there's always ways to kind of work your way around that, which is a bit peculiar and mathematical in some sense. You could say the way it changes might itself be a function of something. So if you take that into account, maybe the whole thing becomes Markov again, but it's hugely complex, so you don't want to care. So it's often much simpler to say just it changes over time, and then it wouldn't be Markov. There's other reasons it might not be Markov, but the non-stationary one is one that pops up quite often. Yeah?
So how much freedom do we have in how we define the returns? So for example, just, the finance investment example, I mean, the return doesn't have to be a return, right? It could also be like, say, some tail return or something, and that way you could also like circumvent the issue of like risk. But is there like any sort of constraint on how we can define the returns?
Yeah, so the question is how do you define the returns, which is actually, you can kind of fold that back into the question of how to define the rewards. For instance, think of, if we take the financial investment example, a natural way to model things is just to give each reward be the difference in, say, money that you have. And then the accumulation of this is the difference between what you had at the beginning and what you had at the end, and you want to maximize that. That's a very natural thing to do. But instead, you might define events. You might say, I'm going to get a reward whenever my money goes above this level. Or I'm going to get a penalty whenever it goes below this level. Maybe you don't care about the exact number. Maybe you don't care about modeling the expected return, of money. But maybe instead you care about some other function of the money. Often you can then fold that into the reward function and relate it to the question earlier about modeling the distributions rather than the expected return. The actual algorithm that does that looks a bit like that. It actually, you can think of it as modeling the distribution by modeling variants of the return, which are more event-based in a sense. Sometimes, though, it's very tricky to set up these events easily. So this is why, for instance, in safe reinforcement learning, people more typically, they still model, say, the expected money, but then they just add the condition that they don't want it to drop below something. It might be possible to phrase the problem differently, where it's more weighted differently, where certain negative rewards are weighted more heavily, say, and that's the reward that the learning system gets. But sometimes it's harder to do that than just to solve it with certain constraints in place. Very good questions. One high-level thing that I wanted to say here is a lot of these things that I've shown right now are basically just definitions. For instance, the return and the value, they're defined in a certain way. And this way they're defined might depend on the indefinite future into the infinite future, essentially, which means that you don't have access to these things in practice. This is just a definition. Later we'll talk about how to learn, and when you learn, we will get back to this interaction loop where you get these rewards one at a time. That means you don't have access to the full return yet, typically. Or you might never actually have access to the full return because it might be infinitely long. But you can still learn if you don't. For now, we're just defining these concepts. And later we will get back to these things, so don't worry as well if you're not quite sure on how you would then use these concepts, because I will explain that in future lectures. So, as a final note on the value functions, much of what we're going to talk about revolves around approximating these. So as I said, this is just a definition of a value function, both of these. One is for a certain policy, the other one is for the optimal value function. I didn't say how to get them or how to approximate them. Now there's multiple ways you would want to approximate these, multiple reasons you want to approximate these. I already mentioned one reason to approximate them is your state space might be too big to actually model these things exactly, to even fit it in memory. So then you might want to generalize across that, as you would typically also do with neural networks in deep learning. Another reason to approximate is just that you might not have access to the model needed to compute these expectations. So you might need to sample, which means you will end up with approximations, which will get better when you sample more and more and more, but they will never be maybe exactly correct. Yes?
Yeah, we were just chatting about this, but with those definitions, would it be possible to be really explicit about what the equivalent Q would be for the dpi and the d star?
Yeah. So I probably should have put Q values on here. So they will come back in a later lecture in which I will have them explicitly. But since I have the V, maybe I should have put the Q. I can tell you what the Q function is for both of these. That might be helpful. For the first one, we're conditioning on a randomly picked action, which comes from your policy, which is a function of S. If you have a Q function, there would be an action on the left-hand side, small a, and we would condition on the action being taken actually being that action. And then on the internal part, where we have this recursion, instead of a V, you could still have this V for the same pi, but alternatively, you could write this down as a summation over actions, and then the probability of selecting each of these actions, and then the associated Q function, state action value, in that next state. Yes. And as I said, I will show those equations later in the course. We will get back to that extensively. In the optimal value definition, essentially what will happen is there will again be an action on the left-hand side, which we will condition on. So the max A then disappears on the outside of the expectation because we've selected an action as an argument to the function rather than maximizing over. But it will reappear inside. There will be a discount times the maximum action value in the next state. But like I said, you don't have to remember that right now. We will get back to these extensively. Thanks. Good questions. So I was talking about approximating these things. And we will discuss algorithms to learn these things efficiently in many cases. So in the case where you have like a small MDP, where there's a small state space, so you can approximate these things in some way. Maybe you have access to the model. We'll talk about that. But we'll also talk about the case where it's a huge state space. Maybe it's pixels, and you have thousands of pixels, each of which can have many different values. And we might still want to learn a value function. And we'll talk about how to learn in those cases. When you don't have access to the model, when you need to sample, we'll talk about that. Whatever we do, when we do get an accurate value function, we can use that to behave optimally. I said accurate here, with which I mean basically an exact optimal value function. Then you can behave optimally. More generally, with suitable approximations, we can behave well, even in interactively big domains. We lose the optimality in that case, because we're learning, we're approximating, there's no way you can get the actual optimal policy. But turns out in practice you don't actually care that much, because good performance is also already very useful. And if it's intractable anyway, that's the best you're ever going to get. So that wraps up the value part of the agent. I'm going to talk a little bit about a model, although we're covering that less in this course. And one reason is that it's actually kind of tricky to learn and use these things. There's also time constraints, of course. But a model basically is just a prediction of what the environment dynamics are. So for simplicity, think of the fully observable case. So the state here is both the environment state and the agent state. It just simplifies thinking about these things, although you can generalize this. Then we might have some function that predicts the probability, say, of the next state for any next state based on a state and an action. You could also predict the expected next state. I chose to write down here the probability distribution, so we're explicitly modeling the distribution of next states here. Instead, in some cases, it's useful just to predict what the expected next state looks like. Sometimes that's not so useful, because maybe in expectation, maybe you're partially in a hole instead of fully in a hole or not in a hole at all. Or maybe you're, the door is partially open and now it's both open and not open in the expected state, which might not be a real state. So in some cases, the expectation doesn't make a lot of sense. In other cases, it does. Maybe the more general thing to do is just to model the full distribution of possible next states for all of the states. Similarly, for the reward, we could have a model for that, which maybe just is dependent on the state and the action, and then predicts what the reward would be for that state in action. You could augment this, maybe make it a function also of the next state, and predict that if you have a certain state, action, and the next state, what would then the reward be? Some cases this is easy. Maybe if you have these three things, maybe the reward is deterministic and you can very quickly learn it. In other cases, it might be stochastic, and in maybe the worst case, it could even be non-stationary. So maybe you want to track rather than to approximate as if it's a stationary quantity. So a model is useful, and we'll talk about how to learn or basically plan with models later. But it doesn't immediately give you a good policy or an optimal policy, because you still need to plan. So soon in the next lecture, we'll talk about how to learn when you do have the exact model using dynamic programming, and we'll learn how to construct value functions. And there are many problems in which this is actually the case. If you think, for instance, of the game of Go, if you're in a certain state, which is basically fully observable, and you take a certain action, you know exactly what's going to happen. You know exactly that if you place your stone there, the stone is going to end up there. Your next state is fully known. In that case, the model is there, and you can use that. In other cases, like a robot walking around, say through a corridor, this is much trickier. And you might not have access to the true model, and it might be very hard to learn a true model. So it's very dependent on the domain whether it makes sense. This is why I basically put down the model as being an optional part of your agent. Many reinforcement learning agents don't have a model component. Some of them do. There's also in-between versions where we might have something that looks a lot like a model, but it's not trying to capture the full environment dynamics, but maybe only part of it. And then maybe you can still make use of this. One last thing I wanted to say about models. Here I had a version that gives you the full distribution. Sometimes it's useful to have that be implicit and instead have a model that you can sample. So we could call that a sample model or a stochastic model, or as it is in deep learning often called a generative model, which basically gives you first state and action, it gives you a sampled next state. Then you could still build a full trajectory. You could sample from that state again. This is something you can't do with an expected state model, because if you have an expected state coming out of your model, you can't necessarily put that into your model again. That might not make sense, because as I said, that expected state might not be something that actually occurs in the real problem. So I'll make these things a little bit more concrete by tossing them into an example. This is a simple example, a simple maze. There's a certain start, and there's a certain goal. And there's only 4 actions. You can basically move up, left, down, and to the right, or north, east, south, west, if you prefer. And the state is basically just the location of the agent, which in this case gives you all the information that you need, because the environment is fixed. It's a little bit weird if you think about it. The state doesn't include any observation on where the walls are, but because everything's fixed, the location still gives you everything that you need to know. We define the reward to be -1 in each time step. There's no discounting. But because there's a -1 in each time step, you're still encouraged to leave the maze as quickly as possible. So what might a policy look like? This is actually an optimal policy for this maze, which in each state, in this case, gives you a deterministic action. In some problems, the optimal policy might be a stochastic policy, but in this case, there's clearly a deterministic policy that will get you out of the maze as quickly as possible. This is maybe the simplest thing that you might need to solve this problem, the policy mapping. I didn't specify how we might learn that, which we'll touch later upon, but it's good to realize that this is the minimum thing that you might need. Alternatively, or additionally, you might learn the value. This is the true value for the policy that I just showed before. Because that policy happens to be the optimal policy, this is also the optimal value function. If I would have picked a different policy, the numbers would have been different, and it would be the value that is conditioned on that policy. The value is here, of course, particularly simple because it's just the negative number of steps before you reach the goal, as you would expect. Note, by the way, that we consider the goal to be when you actually exit the maze, so that final step there has a reward of -1 because you still need to take that action of leaving the maze before you stop. And then basically the problem there terminates. So these returns that we saw before, which I had trailing off into potentially the infinite future, in this case they're actually finite. And they're at most 24 steps. So a model in this case might also be quite simple. So the reward model is just a -1 on each of these states. A transition model is also quite simple. But in this case, in this picture, a part of the maze is missing, which is meant to illustrate that maybe we only have a partial model, or our model is only partially correct. In one of these states, there's basically a connection missing that was here. Maybe because your model just has never learned that. Maybe you've never taken that action, and maybe your model by default assumes that there's a wall unless you've taken that action and you've seen that there isn't a wall. Given this approximate model, you could still plan through it, and you would still find the same optimal solution, even though the model isn't fully correct in all states. In other cases, of course, your model might be approximate, and there might be a wall where there isn't a wall, and you might find a completely different value and a different policy, which might not be appropriate for the true problem. So if we then categorize, and this is also to get you acquainted with the language used for these things in the literature, there's many different ways you can build an agent. It can have any of these components, or it can have many of these components. And there's also the difference between whether the agent has a component and whether it has it explicitly. When I say explicitly, it means it has some approximation. It has an actual function inside that you can use to compute something. So when we say we have a value-based agent, what I mean there is that the agent internally has some approximate value function that it uses to then judge which actions are better than others. There might not be an explicit policy in that case. And in fact, when I say value-based, I mean that there's not an explicit policy, but that we construct the policy from the value whenever we need it. Alternatively, and maybe this is the simplest example, there could be a policy-based agent, which just has a representation of your policy, some mapping from states to actions, and doesn't have an explicit notion of value. The terminology actor-critic is used when an agent has an explicit policy and a value function. This is a little bit, it depends on who you ask and which literature you read, because sometimes people say actor-critic systems also imply a certain way of learning these things. But I'm just going to use it whenever you have an explicit representation of your policy and value and you're learning both, then I'll just call it an actor-critic system for simplicity. Where the policy is the actor and the value function is the critic. Separately, there's this distinction between having a model-free agent and a model-based agent. Basically, each of these from the previous slide could also have a model. That's the distinction here. And when they do, we could say it's a model-based agent. So you could have a model-based actor-critic agent, for instance, or a model-based value agent, a value-based agent. These things are, of course, a little bit more gray than I'm pointing out here, because you could also have these partial models or things that you can interpret to be a model. In fact, some people would say, hey, a value function is actually also some type of model. Sure. But when I say model in this case, I mean something that tries to explicitly model something of the environment that is not the value, and it's not the optimal policy. So that looks a little bit like this, where there's these three components, a value function, a policy, and a model. And then when you have the overlap, say, of a value function and a policy, we would call it an actor-critic. And actor-critics can also be part of that lower circle, which is the model circle. So you could have an actor-critic with a model. But it could also be model-free, which is everything that's outside of the model circle. So you could have a model-free actor-critic, or you could have a model-based actor-critic. You could have a model-based value-based agent and a model-based policy-based agent. You could also just have a model. And as I said, then you still have to plan to get your policy. But in some cases, this is the appropriate way to solve a problem. We'll mostly cover the top end here, where often there's not a model, but even if there is a model, there will typically also be a policy and or a value function. So that's the high level view. So now I'll talk about a few of the challenges in reinforcement learning. And I've talked about a few of these already, but it's good to be explicit. So there's two fundamentally different things that we might do to solve a decision problem. One is learning. The environment is initially unknown. The agent interacts with the environment and thereby somehow comes up with a better policy. You don't need to learn a model, as I said, and I'll give examples of algorithms within this course that don't learn a model but still learn how to optimally behave. And separately, there's something called planning. When we say planning, planning is a hugely overloaded term. It means many things to many people. But when I'll say planning within the notion of this course, I mean that a model of the environment is given or learned, and that the agent plans in this model. So without external interaction. The difference here is the sampling bit, right? In the planning phase, you don't sample, you're just thinking. So sometimes people use words such as reasoning, pondering, thought, search, or planning to basically refer to that same process. The fact that it could be on an approximate model here is important because you typically don't have access to the full model of the environment in the problems that we care about, that we will consider. In some cases you do, and then planning techniques, there's a huge literature with very efficient and very good algorithms that can solve these problems where you have a true model. However, one thing to be aware of is that oftentimes these algorithms assume that your model is true. And that means that if you're going to plan with an approximate model, you might end up in a situation where your planning algorithm finds this very peculiar policy that happens to walk through a wall somewhere because it has mismodeled the fact that that's a wall. You could maybe make these planning algorithms more robust to model errors, and this is an active area of research, but we won't have time to go into depth in this course into that. A separate distinction that is often made, and it is useful, the terminology is very useful, is the distinction between prediction and control. This is not actually a dichotomy. Both of these things are important and can be important at the same time. But the terms are important because we'll be using them a lot, and people in the literature use them a lot. Where prediction basically just means evaluate the future. So all these value functions that we talked about, those are predictions of something, in this case of the return. A learned model is also a prediction. It's a prediction of the dynamics. Control means to optimize the future. And this difference is also clear when we talked about these definitions of these value functions, where one value function was defined for a given policy. So this would be a prediction problem where we have a policy and we just want to predict how good that policy is. And the other value function was defined as the optimal value function. So for any policy, what would be the optimal thing to do? That would be the control problem, finding the optimal policy. We are mostly concerned with the control problem. We want to optimize things, but in order to do so, sometimes it makes sense to predict things, which are not necessarily optimizing. So it's good to keep that in mind, that sometimes we're optimizing, sometimes we're not optimizing, we're just predicting. This also means that sometimes strictly supervised learning techniques are very useful within the RL context. Sometimes you just want to predict certain things, and maybe you can just use supervised learning, and then all the tricks that you can leverage, all the new tricks that you can leverage to do that efficiently. And that can be very useful. Also, they are strongly related. If you have very good predictions of returns, it's typically fairly easy to extract a good policy. You could do this in one shot. If you somehow manage to predict the value for all the policies, you can just maybe select the best policy. Of course, in practice, this is not very feasible. There's an algorithm that we'll talk about later which iterates this, where you basically have a policy, and then you're going to predict the value for the policy, and then you're going to use those values to pick a new policy, and then you're going to predict the value for that policy, and there you repeat these things over and over. This is called policy iteration, and we'll get back to that later. And it's an efficient way or an effective way to improve your policy over time by using predictions. So here's another thought nugget, similar to ones we had before. This is a question for you just to ponder. I'm not claiming I have the answer, but if we could predict everything, do we need anything else? Is there anything missing from a system that can predict everything in order to have, say, full AI? So now most of this lecture wasn't about how to learn these things, but most of the course will be. And for that, it might be important to note already that all of these components that I've talked about are basically functions. Policies are functions from states to actions. Value functions, it's already in the name, map states to values. Models map states to states, or distributions of states, or rewards, or any subset of those, or superset. And state updates, which we haven't talked about that much, but or at least how to construct them, they're also functions. They create a new state from your previous state. We talked about a version where this was given. There was an example here where you augment your observation with some prior observations, but maybe you can also learn how to efficiently build your state. In practice, this means that we can represent these things, for instance, as neural networks. And then we can maybe use all the deep learning tricks to optimize these efficiently. If we have a good loss and we have a strong function class, such as deep neural networks, maybe this is a useful combination. And indeed, we often use the tools from deep learning in what we nowadays call deep reinforcement learning to find good, efficient approximations to many of these functions. One thing to take care about is that we in reinforcement learning will often violate assumptions that are made in typical supervised learning. For instance, the data will not typically be IID. There's different reasons for that. IID meaning, of course, identically and independently distributed. So why won't it be that? Well, one reason is your policy will change. So even just the fact that you're changing your policy means that the data will change, which already makes your problem non-stationary and non-IID. So that's a challenge for typical supervised learning techniques. So you need to do tracking, perhaps, instead of just trying to fit certain data. The stationarity itself might also come back into other ways. For instance, maybe not just your policy changes, but maybe also your updates change. Or the problem itself is even non-stationary. For instance, there might be multiple learning agents in a single environment. And that makes everything very non-stationary and very, very hard. But interesting. So the takeaway here is that deep reinforcement learning is a rich and active research field. Even though the beginning, especially of this course, will mostly focus on reinforcement learning without talking too much about the connection to deep learning, I will occasionally, whenever appropriate, make those connections. And it's good to keep in mind that we might use many of the techniques, but you have to take care when applying them, because you might be violating certain assumptions that were made when the techniques got created. Also, one thing maybe to keep in mind is that current neural networks are not always the best tool, but they often work very well. A lot of work in reinforcement learning has been done in the past on tabular and linear functions, which is much easier to analyze and is also already a pretty rich setting where you can do many things. These days, a lot of people prefer to use deep networks because they're more flexible and they tend to fit weird functions more easily. But it's good to keep in mind that it's not the only choice. And you could sometimes be better off having, say, a linear function, which might be stabler in some sense, might be easier to learn. But then maybe your function class is limited, maybe it's less flexible, and maybe this somehow hurts you, except if your features are sufficiently rich. But maybe then you want to create your features somehow, and maybe that's something that you don't want to think about, or maybe you can't think about because you don't know enough about the problem. So it's just something to keep in mind. So here's an example of how that then looks for Atari. So as I said, there was one system that basically learned these Atari games. That system assumed that the rules of the game are unknown. So there was no known model of the environment. And then the system would learn by just playing the game and then directly learn from the interaction. So what that means, the joystick is now basically what defines the action. As I said, the agent wasn't like the avatar you saw on the screen, but it's actually the thing that pushes the buttons on the joystick. And then that goes into the simulator, which in this case is a simulator of these Atari games. That outputs a reward, which in this case was extracted as the difference of the reward that you can also see on the screen. And the observation would just be pixels. In this case, it would be a concatenation of a few pixels, because actually in these Atari games sometimes, say, the screen flickers. So you might have individual observations in between that are just completely black. And just to avoid that being a problem, instead we keep a very short history of a few frames. Also, this helps in certain games. You might know the game of Pong, where you basically have two pedals where a ball goes from one to the other. If you have more than one frame, you can use that to judge which direction the ball is going. Whereas if you only have one frame, you cannot actually distinguish which direction the ball is going. It would be partially observable. In Atari, you could also plan, assuming that the rules of the game are known. In that case, you could query the model, and in each state, you could just take all of the different actions, see what all of the next states are, and then see what the reward along the way was. And then you could build this huge tree and just plan search within that tree. In the original Atari emulator that we used to do a lot of experiments, the actual emulator was deterministic. The games are deterministic. So if you're in a certain state, you take certain action, always the next same thing happens. In a later version of the emulator, they actually add a little bit of noise by making the actions stochastically last a little longer or shorter, just to break certain algorithms that heavily exploit the determinism of the environment. Because eventually you want algorithms that can deal with situations that aren't deterministic. And most of the work on these Atari games has actually used algorithms that work just as well when the environment is not deterministic. But there are certain algorithms that you can do when the environment is deterministic that you can't do when it's stochastic. So just briefly, before we wrap up, one other thing that I wanted to mention. This will be the focus of the next lecture. So I'll talk about it much more in depth, which is also something that's quite central to reinforcement learning. As I said, we're learning from interaction and we're searching actively for information. So this is sometimes called the dilemma between exploration and exploitation. Because as you're learning, you'll learn more and more about the problem that you're trying to solve. You'll get a better and better policy, and it will be more and more tempting, perhaps, to just follow whatever you think is best right now. But if you do, you basically stop getting new information about things that might still be out there. So what you want to do is sometimes pick actions that you've never done before. This is because you don't automatically get all the data. You actively have to search for the data. And there might be, for instance, there might just be a treasure chest around the corner. And if you never go there, you will never know. So maybe eventually you want to make sure that you eventually sometimes go to places that you've never seen before. That's called exploration. But you also don't want to just jitter all the time. You don't just want to do random stuff all the time because that will hurt your performance, will hurt your rewards. So when you do something that you think is good right now, that's called exploitation. And the balance of these things is actually quite tricky to do in general. So in the next lecture, we'll discuss many methods that can do that. So the goal here is to discover a good policy from new experiences, but also without sacrificing too much reward along the way. The new experiences part is the exploration. The not sacrificing reward is the exploitation. Also, think of an agent that needs to walk, say, a tightrope to get across a ravine. In this case, you might want to exploit a policy that can already walk across the tightrope and then only start exploring when you are on the other side. So this shows that in some cases it's very good to exploit for a little bit to even get to the situations where you can effectively then explore. So these things are very intertwined. But I'll talk much more about that. So summarizing what I just said, exploration finds more information and exploitation exploits the information you have right now to maximize the reward as best as you can right now. It's important to do both, and it's a fundamental problem that doesn't naturally occur in supervised learning. And in fact, we can already look at this without considering sequentiality and without considering states, and that's what we'll do in the next lecture. Simple examples include, if you want to say find a good restaurant, you could go to your favorite restaurant right now, and you'll be reasonably reliably, you'll get something very good. Or you could explore and try something very new, and maybe it's much better than anything you've ever seen before. Or maybe not. So exploration is a little bit dangerous, perhaps. Another example, oil drilling. You might drill where you know the oil is, but maybe it becomes less and less. Maybe it becomes more and more costly to extract. Or maybe sometimes you want to try something completely new. And in game playing, you'll just want to try new moves every once so often. But there's essentially examples of this in any decision problem that you can think of. So finally, before you wrap up, I wanted to go through a little example once more, which is a little bit more complex than the maze example that I gave before, to make sure that these things are a little bit clearer. This is a very simple grid, and the agent walks around, and it gets a reward of -1 when it bumps into a wall. So we can then ask a predictive question. We can ask, if you just do things randomly, if you randomly move around this grid, what is the value function? What is the expected return conditioned on that policy? Now, there's two special transitions here. Whenever you're in state A, you'll actually transition to state A prime and you'll get a reward of 10. This is the highest reward you can get in this problem. If you're in state B, you get a reward of 5 and you go to B prime. Now, it might not be immediately obvious which one of these is preferred, because one has a lower reward, but it also puts you less far away, so it might be easier to repeat that often. Whereas the other one gives you a higher reward, but it's a longer jump that happens after you make the jump from A to A prime, so it takes you longer to get back, and then it's unclear which of these things is preferred. In order to even talk about which things of these are preferred, we need to talk about the discount factor, which trades off the immediacy of high rewards to high rewards later on. And in this case, the discount factor was set to 0.9. This is kind of an arbitrary choice, but it means that there's the value function that is now conditional on both the uniformly random policy and also on the discount factor that we picked, which basically, together with the reward, defines what the goal is. So the goal here is not just to find high reward, but also to do it reasonably quickly, because future rewards are discounted. Here, under B, the value function is given. It's a state value function for the uniform random policy, and what we see is that actually the most preferred state that you can possibly be in is state A, because you'll always reliably get that reward of 10, and then you'll transition to A prime, which has a negative reward, but the negative reward isn't that bad. The reason A prime has a negative reward is because your policy is random and it will bump into the walls occasionally. So you get some negative rewards. And because that state is fairly close to the edge, you'll bump into it more often than if you're further away from the edge. Note, by the way, that the value of state B is higher than 5. You get a reward of 5 whenever you go from B to B prime, but because the value of B prime is positive, the value of being in B is higher than the value of just the immediate reward. Whereas the value of A is lower than 10, because the value of the state it transitions to is negative. Now we could also ask the question what the optimal value function is. If we could pick the policy in any way we wanted, what would be the policy and what would be the value of the optimal policy? Now if you first look at the right-hand side, you see that in states A and B, all the actions are optimal. This is because we've defined them to be all equal. Right? Any action you take in state A, you'll jump to A prime. Doesn't matter which action you selected. So we don't care which one you take. And we can see there's a lot of structure in the policy as well. So probably if you were going to do some function approximation, you'll probably be able to generalize quite well, because the policy is actually quite similar in a lot of similar close-by states. So this is a very simple problem in which you probably don't need to do a lot of function approximation. But in a much bigger problem, let's say you're in a corridor as a robot, and your optimal action right now is to move forward through the corridor. Probably on the next step, your observation is probably very similar, and you'll just continue going forward because of generalization. The optimal value function is now all strictly positive for the simple reason that the policy here can choose never to bump into a wall. So there are no negative rewards for the optimal policy. It just avoids doing that altogether. And therefore it can go and collect these positive rewards. And now notice as well that the value of state A is much higher than 10, because it can get the immediate reward of 10, but then a couple of steps later, it can again get a reward of 10, and so on and so on. These are discounted, so it doesn't grow indefinitely to infinity, but it does get repeated visits to these things. Again, by the way, state A is preferred to state B, which is a function of both of these rewards along the way and of the discount factor. You could trade these things off differently. So I have a video to show all the way at the end, but before I do, I just wanted to give you a high-level overview of what the course will entail. We'll discuss how to learn by interaction as the main thing. And the focus is on understanding the core principles and learning algorithms. At some points during the course, I will give nuggets of practical or empirical insights whenever I have them. And also at the end of the course, we'll have guest lectures by Vlad and Dave, who will talk about their work, which will also include some of these nuggets. But on the whole, we'll mostly be talking about this on a fairly conceptual level. But it's not that far removed from practice. And I'll point out whenever I can how to make these things real and how to actually make them work. Also, there will be assignments, as you know, which will allow you to do that and try that out. So the topics include, next lecture I'll be talking about exploration in what is called bandit problems. A bandit is basically, it comes from the one-armed bandit, which is a slot machine, where you have this one action and you get a random return each time you try that action. This has been generalized in the literature to a mathematical framework which is called the multi-armed bandit problem, where basically you can think of this as there's multiple actions you could do, multiple slot machines, each of which gives a random reward, and your job is to decide which one's best. There's no state, there's always the same slot machines, nothing changes, there's no sequentiality in the problem. So the only problem here is one of exploration and exploitation, how to trade these things off, and of how to learn. How do you learn the value of these things? But that's fairly simple in that case. Then later on we'll talk more about Markov decision processes. I touched upon these a little bit, but I'll talk about how to plan in those with with dynamic programming and such. And we'll move towards model-free prediction and control, where we're not going to assume we have the model anymore, and then we're going to have to sample. There will be something called policy gradient methods, which is a family of algorithms that allow you to learn the policy directly, which we'll talk about. And we'll talk about challenges in deep reinforcement learning, how to set up like a complete agent, how do you combine these things, and how to integrate learning and planning. Are there any questions before we wrap up? Yeah?
When's the first assignment ready?
I don't know. It's on Moodle somewhere. I used to know, but I don't want to commit to saying a date and then having it wrong right now. Other questions, admin or topic related? Yeah.
Moodle said start this week.
The assignment will be out at this time.
Yeah, said it was starting this week.
Right. Oh yeah, I thought the question was when it would be due, not when it was. Ah, okay. So if Moodle says start of this week, it probably should be. But I'll have to check where it is. But thank you for noting, because that's important. And we need to then, if that schedule is correct, we'll need to make sure that it gets out as quickly as possible.
Follow-up question is when would it be due?
Yeah. So if it was due to be out beginning of this week, then we'll also have to check whether the due date is still correct. Because maybe then it has to postpone, but I'll need to check the schedule and check with the people who should have released the assignment. So, thanks. It's very, very important. Other questions?
The link to the book isn't working.
Oh, the link isn't working? Yeah, that sometimes happens, I think. I may have gotten the link wrong. That's one option. Also, in my experience, his site doesn't always work. But
I found it.
okay. If you just Google for Sutton Bartow 2018, you should be able to find the book, or add reinforcement learning if you run them, we're very, very sure. But then you should be able to find it.
The slide in Moodle is different from the slides you present now, so we have to update version.
Yes. Yes, I'll make sure that the slides are always updated. Yeah. I'll try to get them. So what's in Moodle right now are basically the slides from last year. And we'll try to update them as soon as possible, whenever possible. So when slides do change, some of them will stay the same, right? But when the slides do change, we'll try to update them beforehand. That didn't work this time, but I'll try to get them in as soon as possible. But be aware that if you now look at the slides already for future lectures, the material might change slightly. But not greatly, mostly, but slightly. So I'll do my best on that. So I wanted to end with this. I'll explain what you're looking at, because it's kind of cool. So this is a learning system, right? There is something here that is learning. So what is learning here? There's something that is learning to control basically these joints of this, if you want to call, virtual robot simulated thing. Now what is interesting about this is that basically otherwise very little information was given to the system. Essentially the reward function here is go forward. And based on the the body of the agent and the environment, the agent has learned to go forward, but also in interesting ways. Specifically note that that nobody put any information in here on how to move or how to walk. There wasn't anything pre-coded in terms of how do you move your joints, which means you can also apply this to different bodies. Same learning algorithm, different body, still learns to locomote. You could put it in different environments. You could also make it walk on a plane rather than on a line, essentially. And it can basically choose to either crawl over things or maybe sometimes walk past them. Again, all of this, it just has one simple goal, which is the reward to go forward. There's a general principle here that when you do code up a reinforcement learning system and you have to define the reward function, it's typically good to define exactly what you want. As you can tell, sometimes you might get slightly unexpected solutions and not quite optimal. So why does anybody know the reason why this agent was making these weird movements? So it might be balance. Yeah?
For memory, because I think the network was stateless.
So
it tries to remember information by body.
that's a very good one. So part of your agent state might be your previous action will be encoded in your observation. So you can use your actions to get you certain memory in certain situations, right? That's a very, very interesting one. Another thing is, I mentioned here, the reward is to go forward. Typically for us, that's not the case. Typically we want to go somewhere, but we also kind of want to minimize energy. We don't want to get too tired. But if you don't have that constraint, you could also get these spurious things, which might help for balance, they might help for memory, but they also might just be there because they don't hurt, right? And that's something that occurs fairly generally in reinforcement learning. If you model a problem, be sure to put in your reward function what you actually care about, because otherwise the system will optimize what you give it, what you ask it, which might not be what you want. In this case, it's okay, right? Because we didn't actually care about this, and it might actually be helpful in this case. I don't actually know, right? It might be helpful for balance. But in other cases, it's quite tempting to put in heuristics and little nudges towards certain things. Oh, if you want to do that, maybe you first should do that. But that's a little bit dangerous, because in some cases, it'll then optimize that thing that you only wanted to be a sub-goal along the way, rather than the true thing you care about. Yeah?
So, does it have you modeled a physical system of, like, you know, gravity? So, could the person just crawl to the other side rather than walk?
Yeah.
Has it found that walking is the best way of going forward rather than crawling?
Yeah, that's a very good question. So why was it running rather than crawling? So there's two reasons for that. One is that the reward is essentially to go forward as quickly as possible, and the other one is the body. If you have a different body, crawling might actually be the more efficient one, or rolling is maybe the more efficient one. There are cool videos online on similar systems where people have done similar things, and there's some old work as well where people use evolutionary methods for all sorts of weird bodies to see what locomotion will be that it finds, and you find very cute and weird ways to locomote, it turns out. Okay, so I think that's all the time we have. Thank you all for coming.